Hello everybody. Today, let us understand what is a Trie data structure and what are its applications, including its time complexity and where it is used. We'll also see how to implement the data structure in C++, starting from the very basic problem of Leetcode 208. So let us understand Trie with an example. Okay, let us say we want to save all these words like a dictionary. Okay, this dictionary will contains only small alphabets from A to Z. So totally there are 26 unique characters. Let us define a node class, okay, with the following two properties. A node is the same node we used in any tree data structure with the left child and the right child. But this time in a trie, we would be having total 26 children because we have 26 different characters. So, so programmatically, we are defining this particular data structure having two properties. That is, one is all the children, which is nothing but a vector of node pointers itself. Okay, these are children, and we will resize this to 26. And at the same time, we are initializing a bool, and we are calling it isEnd. We'll see later where this boolean is used, but for now, this bool is used to see if a word is ending at this particular node or not. Okay, so we will insert each of these words into the trie and see how it works and how it is defined. We initialize the trie, we create a root node, okay, and this node initially will have all the null pointers, 26 null pointers. Now, when I want to insert a word far, the first letter, we will insert each character by character. So for F comes at location 5. What I mean by location 5 is if A is at 0, B is at 1, so on, F would come at location 5. So at the fifth child index, we will create a node. Okay. When we create a new node, our constructor will always initialize 26 child pointers and will keep isEnd as false, as F is not really end of a word. I'm writing here F because it is coming at the fifth from the fifth child pointer. Now after F, I want to insert A. So here I will create another node A, and A is at 0. That's why it's at the first child. Now for after A, we have R. R is at location 17. So for 17th child, we would be having R over here. And as this is the end of the node, here isEnd boolean would be set as true. That's why I'll just point out with the ends with a green color marker. Okay. Similarly, now when I want to insert farm, I'll come from the root and I'll see, okay, F node is already present, very good. A is also already present, very good. Then from A, R is also present. And now at M, all are null pointers and nothing is present. And M would come at index 12. So at index 12 of this particular node, I am creating a new node. That's as it is coming from index 12. This corresponds to letter M. And this is the end of the letter farm. So I will change the is boolean associated with this particular node as true. Hence, farm is inserted. Similarly, when we go for fare, F-A-R-E, we are creating the node for E. Okay, and fare is also end of the word. That's why this is the end. Now for find, we have from the root will come. F is there. I is not inserted. So we create a new node for I. Okay, now N, like all of the indices we know, N and empty pointers, and for D. And D is the final letter, so we are marking it as green. And farce and fast similarly, F-A-R, C is not present, so we will create a node C, and from the node C, we are creating node E, and this is the end. So farce is inserted, and finally fast, F-A, then there is no S node. This is a null pointer. We are creating a new pointer. For S, the index would be at 18. So at 18th child, there is S, and for T, index would be at 19. So the 19th child of node S would be T. And this is the end. Okay, so this is how we insert elements into a trie. Okay, so at the end, we see the trie is nothing but a multi-child tree. Each tree node has a fixed number of children. In our case, it is 26 number of children, and presence and absence of the children indicates if the key exists or not. So, what are the advantages and time complexities of using a trie? Now, as we can see, for inserting a word in a trie, we have to traverse each and every letter of the word. So this is order of length of the word for inserting. Okay. Similarly, this is for insert, and for delete as well, it would take order of L. Time find time to find if a word exists or not. Again, we'll try to traverse the given word. For example, if you want to find if the word uh, fair is present, Fair. So I'll come to Fa. Then here we figure out that there is no I node present, and we can say it is not there. In worst case, so searching if a word is present or not, worst case would take order of L, where L is the length of the word. Okay. So from here, from about time complexities, you might be wondering, isn't a hash map better suited for these kind of operations, as insert, delete, or search in a hash map would take O of one time itself in a constant operation? That is very true. True. The real power of using a trie comes when we are dealing with prefixes. For example, if I want to find all the words starting with maybe FA, here I would start with F, then go to A, and I would only search in this particular subtree for all the green nodes. Green nodes, I mean, where the words are ending, and I can get the set of words which start with the prefix FA. But if the same thing, if I have to do in a hash map, there is no other way, but I have to iterate through each and every key. So in those cases, our trie is very, very useful. So some of the applications for the trie would be for auto suggesting. For example, in the browser, when I type N, automatically it suggests me Netflix. So somehow it knows that with this given prefix, I might probably be looking for this one. So this is one example. In routers, it is used for longest prefix match. Okay. And for the computer science students, there is a very famous problem based on trie called max XOR. So given a vector of numbers, we want to find two numbers which has the maximum XOR. So later we'll see one of the problems. I will make a video on this as well. But that's a very famous question. And if you have a lab exam on DSA where trie is included, you might expect this question to be there. So let us see how to code this whole data structure for inserting, searching, and finding. Okay, so let us see how to implement a trie in C++. First, as discussed, we need a new node class. Okay, so we'll define a class node. And in this, we have two properties, and both of them are public. Okay, the node properties are vector of node pointers, and I'll call it as child. And another property is a bool, calling it is end. Now, in the constructor of the node, constructor is writing the same name as the class. We are initializing this particular node child property. I am resizing it to size 26 because A to Z, and all of them are null pointers when we initialize a node. And all the nodes are by default is not the end of a word. So I will keep it as false. Our node class is defined. Now, whenever a tree is initialized, we want to create a root. Okay, so the root node is equal to new node. Great. And this root should be accessed by every other function. So it should be a property of the class itself. So we will say a root is a node star type root. Okay. Now we'll see how to implement the insert function. First of all, I want to know at which node I am at right now. So current node, I will always start from the root. Okay, now for each character, for character C in the word, for getting the index of the particular character C, I'll do like this one. Integer idx is index is the current character minus character A. Now if C is A will get 0, B will get 1, and so on. Okay, so if at my current node itself, current node's child at index idx, if this is equal to null pointer, that means we need to create a new node at this particular index. So my current node's child at idx index, I have to create a new node. Okay, the new node has been created and I have to move forward. So my current node should become the next node, like whatever has just been created, that is child idx. Okay, else. Else is that means we don't have to create a new node. This already exists. So if it exists, I just have to move forward, copy from that particular location. So I just need to copy this line and paste it over here. So current node has shifted to the next one. And at the end, when everything is finished, that means I'm pointing at the last letter of the word. I will set the is end of this particular node as true. Great. So this is the logic for insertion. We'll see search. Now I want to search if this given word exists in our trie or not. Similar, like just like before, we need where we are standing at. So our current node is equal to the root node for auto C in word. That means each character of the word, I'll get the index as the previous insertion step itself, the current character minus character A. Okay, so if my current node's child idx is equal to null pointer, that means this particular letter does not exist. So I can return false immediately as the word does not exist. If it exists, I will move forward. That means current node is equal to current node of the child idx. Yes. Now, after traversing this much, we also need to check that the last node at which I am standing, is it the end of the word or not? So if current nodes is end is equal to true, we return true, that this word exists. Otherwise, we return false. Okay, this step is important because there might be cases where, for example, I have inserted word as backlog and I am searching for just back. So in the tree would follow until k, but k is not the end here. Okay, so in those cases, we need to check if the current node is the end or not. But for the same function of starts with, I just want to see if is there any word with this particular prefix. That means this is very similar code as the above one. I can more or less copy paste this one. Okay, copy paste this one, but this condition is not needed. If at all I am traversing until the end of the word, that itself is enough. I can return true. The only thing is here the string given is prefix, so instead of word, I can write prefix. Okay, I hope you understood the difference between this function and this function. The only thing is the end of the word doesn't have to be is end as true for it to be a prefix. Let us run and see. Okay, and let us submit. Okay, it is accepted. Thank you so much. Please subscribe to my channel.